Hey gang, let's talk about a particular type of discrete random variable, one that is called a binomial random variable. So we looked at discrete random variables in previous videos where each outcome of the variable had a specific probability that was explicitly specified. Refer to that coin flip example. And that's also the case here with a binomial random variable, but these types of variables have specific properties that make them quite nice, actually. And a binomial variable, maybe that word binomial, the prefix bi, hopefully reminds you of some quantity bi. A binomial variable applies to a variable where there are two possible outcomes. We often call those outcomes success or failure. And it's not necessarily good or bad, it's just usually we're keeping track of the successes and whether they occurred or didn't. A binomial random variable also has the property that the probability of those successes are constant. They're not changing. There are a fixed number of trials. I see I spelled trials wrong. So for instance, like a coin, there are two outcomes, heads, tails. Every time you flip a coin, there is the same probability for the heads or for the tails. And if you're going to flip a coin for a certain number of times, you're just going to stick to it. Furthermore, each coin flip is independent. So you put those four criteria in a basket and you've got a binomial random variable. The probabilities that define a binomial random variable can be described in a probability distribution where the probabilities actually follow a formula. So we'll take a look at that formula here in a second. And just a reminder of some notation, we'll write it all out. But n is essentially the sample size, and we sometimes consider that the number of trials, kind of a slightly different perspective. And in a specified number of trials, what we're keeping track of here is how many times a success occurred. So was there 0 successes, 1 success, 2, 3, 4, 5, 6 successes? So this formula for the binomial probabilities, probability of your random variable achieving a certain number of successes, lowercase x, is, now leave a little space here because I like to do this sort of backwards. Well, we need the probability for a single success, but then that must be raised to the number of times that success occurs. And because of the property of independence, that allows us to multiply probabilities. But if you succeed a certain number of times, then the number of failures must be incorporated, and this would be the failure rate, and we will raise that to the remaining number of trials. Then we need to incorporate how many different ways can we achieve x successes in a larger group of n trials. And we saw in a previous video that the combination n choose x will allow us to do that exactly. I would like to have a little legend or key here for all these letters. Regular P is the probability of a success, but that would be in a single trial. In a single trial. It's not the same when we're considering multiple trials, but we will get to that. Since there's only two outcomes, we know that 1 minus p is the complement to the success probability, so that would be the probability of a failure, also in a single trial. What other letters do we have? X is the number of successes. X can take on values such as 0, 1, 2. These are whole numbers because we're in a discrete world. 3, however many successes, but you could not have more than n successes. Let's see, n, therefore, is the number of trials. Another perspective of sample size, essentially. N, choose x, which is, we saw this formula in the previous video, n factorial, it's the big number on top, small number factorial on the bottom, and also on the bottom, big minus small quantity factorial. And this is the number of ways to arrange x successes in n trials. And we saw how to calculate this not only with the formula, but with the help of a calculator, so feel free to reference the combination video. If we just quickly review, remember when we had the coin flips and we had 3 flips, and we thought, well, how many ways could you get 1 tail? And we said, oh, you could get a tail on the first flip, or a tail on the second flip, or a tail on the third flip. A coin is a classic binary situation, and here there are 3 ways that in 3 flips you could achieve 1 tail. So that's exactly what this combination would tell you. That would be 3 choose 1. In a group of 3 flips, how many ways could you have 1 success? There's 3 ways. So hopefully that sufficiently jogs your memory. Let's crank into an example here. The best examples are about cats. So let's suppose that we selected 3 cats at random from a population of cats in which 37% have the polydactyly condition. Are you familiar with what this condition is? Well, let me show you a Google image search here. This is polydactyly cats. And poly, as a prefix, you might know what that means. Dactyl for digits. So these are when there are extra digits usually. So look at this kitty's paw. Oh, and your face is charming. Okay, you can have fun with that all day long. Let's talk about these cats. So let's define the random variable. We'll use the letter x, and x will represent the number of cats with the polydactyly condition. And we should maybe verify that x is a binomial random variable. Is X a binomial random variable? Well, let's go through the 4 criteria. Are there 2 possible outcomes? Yes. Either a cat has the condition or a cat does not have the condition. So here a success is a cat with the condition. Next up, what is the probability of this success, and is it constant? Well, the only value for probability that could be possible here is that 37%. So we will call that the success probability and assume that it is constant. Next are the trials independent. Here, each of the 3 cats would be different trials. And since they are randomly chosen, we will assume that the outcome of whether or not a cat has the condition or not is considered independent. So I'll just write each cat independent. As a genetic trait, if we were only sampling cats from a certain family line, then that may be violated. And lastly, fixed number of trials. Yes, fixed number of trials. And how many trials is that? 3 cats. So that is n equals 3. So that's not changing. 3 cats, always. Okay, so we've got our binomial random variable. Yes. Let's determine some probabilities associated with this binomial random variable, and we'll use that handy dandy formula from above. But first, I'm going to make a little table to help organize our work. You know I love my tables. In this table, I've got 3 columns. The first saying the number of cats with the condition, the number of cats without, and then the probability for such. So we're going to fill this all in. These first 2 columns we'll be doing right now. So the number of cats with the condition, well, those would be our successes, right? So we can have potentially 0 cats with the condition. So that would be 0 cats. We could have 1 cat with the condition, or 2 or 3 cats with the condition. And because these are disjoint events, therefore the number of cats without the condition is going to be 3, 2, 1, 0. And now we're going to find the probabilities for these values of successes. We're going to need that formula from above. I'll copy and paste it below. Okay, I've copy pasted our formula from above, and we're going to start finding these probabilities. Let's start with the probability of exactly 0 cats with the condition. So that is 0 successes. X equals 0. So we know what value we'll plug in all throughout here. Furthermore, the values for n and p are fixed, right? P is constant, n is fixed. So we now know all the values that we need to plug in for this question. So here we go. Probability that the number of cats with the polydactyly condition is 0 is n choose x, 3 choose 0. That's a nice number from when we introduce combinations. P 0.37 raised to the 0th power times the complement 1 minus 0.37 to 3 minus 0. Okay. We can certainly and probably should use a calculator to help us with some of these calculations. However, in a group of 3, how many ways are there to select 0 cats? There's only one way to do that, so I don't need a calculator for that. 0.37 to the 0th power is also a 1. Don't need a calculator there. And here, let's go ahead and perform this computation. I would like a calculator, please, to take 0.63 to the 3rd power, approximately 0.25. And I'll put that in our table up here. Excellent. Moving right along, let's find the probability that exactly 1 cat has the condition. Okay, so notice the answer here is not 0.37. That is not the answer. 0.37 is the chance that 1 cat out of a group of 1 has the condition. This is a question about 1 cat, any 1 cat in the group of 3 with the condition. So let's backspace U. Number of successes here is x equals 1. We now know what to plug in to every portion of our formula. I will scroll down a click. Probability that the number of cats with the condition equals 1 is 3 choose 1 times p to the 1st power times 1 minus p to the remaining number of cats, which is 3 minus 1, which is a 2. Before I go right into my calculator, I will simplify what I can. 3 choose 1. How many ways can you choose 1 cat out of a group of 3? Well, it could be the 1st cat, it could be the 2nd cat, or it could be the 3rd cat. There are 3 ways that can happen. This is 0.37 to the 1st, not much simplification there. And here we've got 0.63 squared. So I will type that all in. Here is our calculator. We'll do 3 times 0.37 times 0.63 squared. To arrive at approximately 0.44. I want to touch on this idea of 3 choose 1 and why that equals 3 again. Here we've got 3 kitty cats. We've got Fluff, who got the short stick on the names, Lucy Clawless, and Tomcat Collins. Don't want you getting them confused, so they've got names. And there are 3 ways that 1 cat could have the condition. Fluff could have the condition, success, but Lucy Clawless and Tomcat Collins may not, F for failure. That is one way. Or Fluff is a fail, Lucy Clawless is a success, and Tomcat Collins is a fail. Last but not least, Fluff and Lucy Clawless could both be failures in the sense they don't have polydactyly condition, and then Tomcat Collins is the success. So there are 3 ways that one cat could have the condition, which is why we multiply over here by 3, because 0.37 times 0.63 squared is not enough. That would be the probability that maybe just Fluff has the success. But we need to incorporate the 3 ways. That's what that combination is all about. All right, let's crunch some more numbers. Hopefully you're getting the hang of this, so I will go a tad faster. Probability of 2 successes is 3 choose 2, 0.37 squared, 1 minus 0.37 to the first. This is still multiplication by 3. Can't really simplify that without the assistance of a calculator. Okay. Finally, the probability that all 3 cats have the condition 3 choose 3, 0.37 cubed, and then this next quantity 1 minus 0.37 will be to the 0th power. So this is a 1 times 0.37 cubed times a 1. So I just need 0.37 cubed, approximately 0.05. And I'm going to go make sure I've written all of these in our table up above. Looking at all these probabilities, these are all the possible outcomes. There are 4 of them when dealing with this kitty cat scenario. Can you see what all of these probabilities must add up to? They must sum to 1, right? Yay. I've got a couple more questions to ask you, and then we'll talk more properties about binomial random variables. Here's the questions. What is the probability that at least 1 cat has the condition? Let's look at this table here. I copy-pasted it. At least 1 cat has the condition. Well, wouldn't that be the probability that x is, okay, we got 1, but we need at least 1. So 1 or greater. So we would use the greater than or equal to symbol. Greater than or equal to 1, well, that would be all the successes, 1 or greater, which correspond to these probabilities. So that's all the probabilities except 0 successes. All except 0 success probability. So I think the easiest way to do that is 1 minus 0.25. Certainly you could have added up 0.44, 0.26, 0.05, but I think my way is a little slicker. So this is 3/4. And essentially what we just used there was a probability property of complements. Next question. What is the probability that more than 1 cat has the condition? More than 1 cat. Probability x1 and more than, so I would need the greater than symbol. And in this case, I need to consider more than one. So I'll use blue here. I need the probabilities that correspond to 2 and 3 successes. So 2 or 3 successes. I need those 2 that I'm putting in a box there. So I will add those up. 0.26 plus 0.05 is approximately 0.31. So there's a distinct difference here between the terminology of more than and at least. All right, we've discussed the probabilities that make up the binomial random variable. Let's talk about the expected value, aka the mean, of a binomial random variable. Because a binomial random variable is discrete, we could write the formula as we did in a previous video where we wrote y times the probability of y. That would work here, absolutely. But because there are only 2 possible outcomes, the mean or expected value is actually much, much simpler. The mean of a binomial random variable is, it's probably the shortest formula you'll see, n times p. That's it. And I think it makes intuitive sense. Example, say we had 1,000 kitty cats from this population, in which 37% again have this condition. Well, wouldn't we expect 370 kitties to have the condition in a sample of 1,000? Makes total sense. Awesome. Well, who's next? We just did the mean. You know who's next, right? Who is the mean's best friend? It's good old standard deviation. And again, we could use that formula that was presented in the discrete random variable video. However, because there's only 2 outcomes, this formula is a whole lot simpler. Standard deviation of random variable, that's binomial, because we're talking about number of successes, so we got to get that involved. But standard deviation would be the spread of those successes. Well, that would be measured by the failures. So we'd have to get those failures involved from the failure rate there. Every time you see standard deviation, you know it's chilling with a square root symbol there. So those are some fun formulas that are much easier to compute than we've seen in the past. Okay, a couple more things I would like to show you is that we can transcribe these probabilities into a graph, like a histogram. And we drew these in the previous video, but I thought it would be funner to do this with a little bit more interesting numbers. So I've got myself some axes here. I will label my vertical axis as probability. I'm running out of canvas space, so I gotta fit what I can in here. And down here we've got capital X, which we know is the number of kitty cats with the polydactyly condition. And we know we can have 0, 1, 2, or 3 cats. And our probabilities, our largest probability here corresponds to 1 success. And I will put tick marks up to 0.5. 0.1, 0.2, 0.3, 0.4, 0.5. Okay, I'm going to make these like we did in a previous video in which it doesn't use bars as much as just single lines. So 0 successes goes up to about 1/4, so right around there. 1 success, largest probability at 0.44, that would be right around here. 2 successes, probability of about 1/4. Gosh, that's going to be just almost inobservably taller than my blue up here. Maybe my blue is too tall. There you go. And then 3 successes, 0.05. That'll be pretty short right here. Cool. Even color-coded. Well, what shape does this have? I would say it's got a mild skew, skewed to the right skewed. And furthermore, I want to notice that the mean here, which for this variable, the mean would be 3 times 0.37, which is 1.11 cats, right, which is closest to 1. I want to note that the bar that is closest to the mean will have the largest probability. Will have largest probability, which is the tallest bar, because it's the expected value. It's what's expected to occur. It's not guaranteed, but it's what is most likely. It's kind of the foundation of expected. One reason why this histogram is skewed to the right is because that largest probability was on the value for 1 cat, right? And that value is towards the left end of the range of values for our variable. Therefore, that right tail was longer. If say our event probability was 0.5, we would have a bell-shaped distribution, because then this would be perfectly symmetric. If, say, our event probability for our kitty cats was 0.9, like 90% of cats had the condition, well then the largest probability would be up here, and then the left tail would be really long. So if that was the case, then this would be left skewed. All right, a lot of fun in this video. We're going to have some more fun with binomial random variables and binomial distributions. So see you there.